Well, hello everyone, and welcome to lecture 8 on the colloid and interface chemistry course. So today I would like to cover a few things to introduce the notion of natural and synthetic polymers, to give you a very brief overview of the types of polymer and the types of polymerization processes, and to introduce the idea of how we can use polymers in colloidal systems, largely to change the stability of colloidal systems. So polymers are very important substances. They're very important in industry. I mean, you think about how often you make use of polymeric substances. Indeed, every time you use something that is plastic, you are making use of a polymer. Now, of course, that can be for good or bad, and indeed, every time we make use of single-use plastic, of course, that's been in the media a great deal over the last 5 or 6 years because of the inability of these synthetic polymers to biodegrade in the natural environment. That poses a challenge, particularly for us chemists, because we need to find solutions and develop new polymers that are able to biodegrade. So they're important from a large-scale commercial perspective, and they are also important on a sort of molecular level in terms of modifying the stability of colloidal systems, and we'll look at those in more detail towards the end of this lecture. So you've all come across polymers before, I'm sure. Fundamentally, they are all just very long chain molecules, and they're made by assembling a series of monomers, or if you like, they can be broken down into monomeric units. And you can get polymers whereby those monomeric units are of the same type, and we call those a homopolymer, or you can get polymers by where the monomers are a mixture of different types, and we call those copolymers. And there are lots of examples of naturally occurring polymers. Rubber is something that occurs naturally in nature from the rubber tree and can be purified into a polymer. DNA is a good example of a biopolymer, as well as carbohydrates. They like to polymerize, and of course we know that in DNA, amino acids like to polymerize. There are, of course, a large number of synthetic polymers. I think polystyrene might be the clearest example that comes to mind in terms of something that we come across quite often. But PET, polyethylene terephthalate, is probably the polymer that you come across most often in your everyday lives, and it's the polymer of choice for food packaging, drinks packaging. If you have a bottle of water that you buy from the shops, then the chances are that comes in a PET or a polyethylene terephthalate package. Indeed, as well, packaged meat and vegetables will likely be in PET, very, very commercially and widely used polymer. There are a number of natural polymers then that we can sort of class. Polysaccharides is one, so whenever you see something like cellulose or starch, that is a polysaccharide. These are natural polymers. Proteins are another key class of natural polymer. and they are, of course, bonded through that peptide bond. Fundamentally, a condensation reaction between a carboxylic acid and an amine. And they're quite interesting molecules because they are very, very large molecules. You think about some of the molecules that you've been making in the laboratory over the last couple of years. Some of the organic species that you've been making are very small on a molecular scale, but polymers are relatively giant in comparison to, a simple molecule. And in theory, the number of monomers that we can join together is unlimited. But eventually the polymer chain will grow so large that stress within the chain will cause them to break up. It's found that those natural polymers that we spoke about, rubber and such like, have around about, on average, 10 to the 6 monomers in a chain. And because nature's so good at chemistry, all of the chains have the same length, so they're all the same size. It's very different with what we can do in the laboratory as chemists. We can make polymers. Generally, you'll find, if you look in the literature, that synthetic polymers tend to have around about 10 to the 5 monomers in their chains on average. But importantly, there's always a distribution in chain length, and that's down to the synthetic processes that we use as chemists to make the polymers, and the fact that we're just not as good as Mother Nature. Now, there are a number of synthetic polymers that we need to be aware of. Addition polymers, condensation polymers, and synthetic rubbers and copolymers. In addition polymerization, monomers add to one another, and this is the key point here. They add in such a way that the polymeric product contains all of the atoms of the starting molecules. So compare that with the natural polymer that I spoke about a few slides ago, the protein, whereby we have a reaction between a carboxylic acid and an amine group, and you lose a water molecule. So you lose some atoms there. That's not addition polymerization. In addition polymerization, the monomer is added to the growing chain and no atoms are lost. There are 3 steps in addition polymerization. There is an initiation, so you've got to start the reaction, and that's often through the use of free radicals. There is propagation, in which the chain starts to grow, and there is termination. Usually, in addition polymerization, you are using free radicals, and the termination step occurs essentially when the free radicals have been used up and you can't grow the polymer chain anymore. Now, I show you that schematically there. You can see that in that initiation step, we form so that's right at the top of this slide, we form a free radical. And that radical is able to go on to the propagation step and react with a monomer. So the monomer here is ethene. You can see that in the propagation step. And that reacts with an ethene monomer. And if you follow the propagation step through, it creates, or it initiates a chain. And there is now a free radical involved in the next step, which is able to react with another ethene molecule and grow the polymer chain. At some point then, there will be a termination step, and it may be when two large fragments meet. So you can see on the termination step that there is a growing chain on the left with a free radical at the end of it, and a chain which has no free radical. When they meet then, suddenly you gain a large terminated chain that is unable to continue in the reaction, and this is generally where the termination step ends and the growth of the polymer chain stops. I show you there a polyethylene polymer. That's just a ball and stick model and a space filling model. That's a good example of a polymer that's made through addition polymerization. There are lots and lots of examples of ethylene polymer derivatives, and these have huge commercial application. So think about some of the polymers that you see there. They're all derived from this addition polymerization process that I showed you a couple of slides ago. There's the classic ethylene polymer, polyethylene. That's the polymerization process that I showed you a few slides ago. And it's used very, very heavily. So we spoke about that at the start of the lecture. Bottles, bags, films. It's found in children's toys. It's used very, very widely in the biomedical industry. Catheters, blood bags, organ bags just to store organs in for transplant. It's very widely used. You can see there are derivatives, so you can add chlorine groups to the polymer chain, you can add cyano groups to the polymer chain, and these will all have slightly different properties and are therefore used in slightly different situations. And there are even more that you can derive. You can see there's a fluoroethylene derivative that's used in non-stick pan coatings, very similar to Teflon. And you can also get polymers that have interesting properties. So polymers that conduct electricity that are now in sort of materials chemistry at least starting to develop a lot of interest and are starting to kind of rival things like graphene within material science. So look at the common theme. These are all polymers that are synthesized through addition polymerization. The common theme here is that there is a lot of unsaturated double bonds. Okay, so there's a lot of pi conjugation throughout these systems. Think about that and compare them to the structures that we've been looking at in our inorganic chemistry studies, and you'll see there are analogies to be drawn between the structure of graphene and the structure of these compounds here. There are a lot of double bonds, so a lot of pi conjugation and the ability to conduct electricity. Okay, so that was addition polymerization. There's also condensation polymerization. So in a condensation process, a small portion of the monomer molecule is not incorporated into the final polymer. So again, to go back to the example I gave you right at the start of the lecture here, the natural biopolymer, a protein, that reaction between the amine and the carboxylic acid yields a water molecule as well. So the two amino acids join, but there's also a water molecule that flies off the end of that reaction. And there we lose a small portion of the monomer molecule that is not incorporated into the final polymer. Now, this is synthetically, the example there is an example of a biopolymer, but something that occurs naturally, but synthetically, these condensation reactions are used to create a lot of polymers of commercial relevance, things like nylons and silicones. So some examples then to show you. Polyester is made this way, and you can see that yields a water molecule. Polyamides are made this way, yielding a hydrochloric acid. Nylon is made this way, and interestingly, Kevlar is made this way. And I'm sure all of you have heard of Kevlar. It's used in bulletproof vests. Nylon, of course, famous story being developed on either side of the Atlantic, New York and London. That's how it got its name. And there are other examples of condensation polymers. Silk is a biopolymer, of course, a natural polymer. It's basically a protein. Polyurethanes are used heavily commercially. They are also condensation polymers. Just an introduction to the notion of elastomers here. These are flexible, elastic materials. They're often polymers. Natural rubber is a good example of this. It's soft and tacky when it's hot, and it can be made much tougher in a reaction with sulfur that we call vulcanization. You can essentially cross-link rubber using these disulfide bridges. So this is an example of what you can do to polymers sort of post synthesis. You can make them even stronger by cross-linking polymer chains. Some of you have done that in the laboratory in 5014. And you can see that the extent to which you cross-link the chains tends to dictate the application and indeed the final properties. So the table that's shown there is a table of a product against the number of monomer units between crosslinks. So the lower that number, the more crosslinks there are, and the harder or the less flexible the final rubber. You can see that in a bicycle tire, you've got lots of these disulfide bridges, lots of vulcanization. And compare that to a surgical glove where you don't have that many crosslinks. And you can see clearly, a surgical glove has very different properties to a bicycle tire, except apart from it's exactly the same material, just less crosslinks. Now, some of the most important addition polymers are copolymers. So these are polymers that are made not entirely from one monomer, but a mixture of two or more monomers. So a good example is styrene butadiene rubber, SPR. which you can see in the image there. It's a copolymer between butadiene and styrene. And it's commonly used in tyres, but interestingly, it's also used in bubblegum when it's not got any crosslinks. Another good example of a copolymer is ABS, polyacrylonitrile butadiene styrene, and that's got 3 monomers within the polymer backbone, and depending on the ratio of each monomer with respect to the others, you can very easily tailor the property of the final polymer for its intended application. And epoxy resin here is another example of a copolymer, very heavily used with other materials such as fiberglass in things like bicycles, and I mean, this stuff is also used in the home. The chances are that your bathtub or the plastic surround on your shower is made of this stuff. And copolymers can be classified in 4 different ways. Have a look at the images there. Start with A. This is an alternating copolymer. So we'll assume that you have 2 monomers minimum in your copolymer. The alternating copolymer is where you have very ordered alternating monomeric units. So it will go, for example, if we have monomer A and monomer B, the polymer backbone or the chain will go AB, AB, AB. You can have a random copolymer by where the distribution of monomeric units throughout the chain are seemingly random. You can have a block copolymer where there are periodic blocks of each monomer throughout the chain, or you can have a graft polymer where you have one of the monomers that forms a backbone, and grafted onto that are sort of smaller chains of the other monomer. There are a number of properties of polymers that we need to be aware of. Thermoplastic polymers are ones that can be softened by heat and can be molded into shapes. Thermosetting polymers become very hard at elevated temperatures. High density polyethylene, specifically for the high density polyethylene class, has a high density and is therefore much more rigid and strong, and also low density polyethylene, so that's much less dense and is much more waxy in appearance. But the important thing is that you can this is a very tailorable process, very flexible process. So polymer chemistry is a huge field, and you can design polymers that have very specific properties for intended applications. There's an example of low density and high density polyethylene and the difference in properties. Okay, so a brief introduction to polymer chemistry there. What I would like you to be able to describe from that section, I'm not going to ask you about examples of polymers. I'm not going to ask you about the different types of polymer. What I would like you to be able to describe is the difference between polymer synthetic routes. So be able to describe the process of the processes of polymer synthesis that I show you or have shown you throughout this lecture. Now, polymers can have a very large impact on colloidal stability, and I'd like to introduce that and frame polymer chemistry from the perspective of the last sort of 6 or 7 lectures. A lot of colloidal suspensions also contain polymers, and polymers are, being large and quite interesting, they will adsorb to the surface of particles, or they can be chemically attached to their surfaces. And they can act a little bit like surfactants or just giant surfactants, and they can have a very large impact on the stability of colloidal suspensions. We've spoken a lot about charge stabilization, and we're going to have a look at this in the laboratory when we come to do the practicals for this module. We've spoken about how you can render stability in a colloidal system by manipulating charge. So have a look at the 2 particles that I show you at the bottom right of the screen there. They're 2 negatively charged particles, and we know that they are not going to want to come into contact with each other because of electrostatic repulsion. So we can stop aggregation of particles through manipulating charge. But there are some limitations in relying on charge stabilization alone, and they are as follows. If we want to rely on charge stabilization, we've got to use a polar solvent. We've got to use something like water. Charge stabilization doesn't work so well if you have a non-aqueous system, so if you have a solvent that's an oil. Particles that are charge stabilized are very sensitive to the addition of salt. They will aggregate in the presence of too much salt. And think about the importance of that. If you're making a detergent formulation that you need to be stable, then often salt concentration can vary depending on where you are in the country. So somebody using a formulation in Chester, for example, where the water is very soft and the presence of salt is quite low, will have a very different experience to somebody using it in London, for example, where the water is quite hard and there's quite a lot of salt. And in addition, these charge stabilized suspensions can't tolerate freeze-thaw cycles. That's really important when you start to think about using them in, for example, the biomedical industry, where you're often freezing drug suspensions, or it's important in the food industry, for example, where you may be freezing and thawing food. So we can use polymers to think about stabilizing colloidal systems, and there are 2 key mechanisms through which you can manipulate the stability of a colloidal system by using polymers. The first is steric stabilization, and the second is bridging interactions. Steric stabilization involves coating a particle with a layer of polymer, and the easiest way to do that is just to use charge interactions or hydrophobic interactions and allow the polymer to absorb just onto the surface of the particle. But you can also chemically graft a polymer onto the surface. If you cover the particle with a dense layer of polymer, then you are providing a barrier to aggregation. So imagine you've got a particle and you coat it with a polymer layer, and they become close enough to allow those polymer layers to touch. So it's a bit like, imagine you are a particle, or you're in a room with a friend and you're both particles, and you just have normal clothes on, and you can approach each other quite closely. If you were to put a big jacket on, or if you were to cover yourself with a pillow, then as you approach, suddenly you wouldn't be able to get as close. This is exactly the same principle here. We provide the particle with a jacket, essentially. Now, as those particles approach, with this polymer jacket, when they get close enough, there are two possible outcomes. The polymer layers on the surface can start to actually intermingle, and they can overlap, or they can start to compress. So let's have a look at those. As the two particles move closer together, there is a local increase in polymer concentration. And from a free energy perspective, that's not stable. So it carries a penalty, and ultimately it gives rise to a repulsive force that separates the two particles. When you think about designing one of these steric stabilizers, so you're thinking about synthesizing or developing a polymer that's appropriate for the particle under study, you've got to think about several things. You want high surface coverage, so you want your polymer to interact heavily with your particle. You want strong adsorption. You don't want the polymer to detach and float off into solution. The solvent you're using is important because you want the polymer chain to be stabilized, and you don't want much polymer in free solution. So in practice then, to go back to the examples that I showed you at the start here, copolymers are the best for this because they have two different types of monomer. Now you can also get these things called bridging interactions, and at very low surface coverage, it may be that polymers attach themselves to more than one particle. And here we can actually flocculate particles, so we can actually destabilize the system through using polymeric interactions. Because they attach to more than one particle, they draw particles in together and aggregate the system. And you can find papers on this where you look at magnetic polymers that act as bridging polymeric flocculants that are used for water purification. Thank you very much.